what I'm writing. Right, so it's going to be a relatively short explanation today, because usually today and yesterday would have been double, and yesterday was probably a little bit longer me explaining than usually I would do. So today is about nuclear energy levels. So what is quite interesting, and not something that you've probably ever come across before, is that when we're talking about the nucleus, they actually have energy levels which are very similar to electron energy levels. So if we're talking about electrons, then we are quite used to the energy level diagrams. And we're quite happy that if you have an electron that moves down, it gives off a photon. And if you have an electron that moves up, it's moved up because it's had to absorb a photon. For the nucleus, it's almost exactly the same. There's actually not really much difference at all, which is really quite nice and simple. We draw them in the same way. But obviously, we're not talking about electrons here. We're just talking about the nucleus as a whole. So I don't know how you want to draw the nucleus, but the nucleus as a whole. And again, it could be raised up, and it could fall down energy levels.
So do you mean here like excite and de-excite?
Yes, I do. Yeah. So if it falls down the energy levels, it again emits a photon.
So can you move it down a bit, please? Thank you.
Now, there's a couple of small differences in that if we're going to label the energy of the electrons, we're probably talking about electron volts, so times 10 to the minus 19 joules. If we're talking about the energy for the nucleus, we're talking about MeV, so 1,000,000 times greater than for electrons. So that is quite a big difference. The other difference is that these photons here, because it's EV and because it's electron transitions, these are going to be anywhere from radio up to X-ray. But these photons, because they're from the nucleus, they are gamma, right? By definition, they're gamma. Even though they might have energy similar to the X-ray, they are still gamma photons. So how do they get promoted up an energy level? So yesterday we talked about beta decay. So let's look at an example. We've got Mg 2712, and this might decay by beta decay to aluminium 2723, plus obviously a beta particle and an antineutrino. Now, we said yesterday a couple of things, didn't we? We said that the beta particles will be formed with this energy distribution. So they have a range of energies, which means there is some missing energy or some extra energy. So some of that energy can go to the neutrino, but it could also remain in the nucleus. So we can promote it by radioactive decay. Or let's use Ali's word, let's use excited, because that's a better word.
So
Yeah.
you see with electrons, sort of when they excite and de-excite, they move through the energy levels, so through the shells.
Yeah.
Does the nucleus just gain more energy so it starts to vibrate faster, or does it actually move?
Yeah.
Would the electrons actually move to a new shell, but where would a nucleus wouldn't move anywhere, would it?
Yeah, so that's a good question. Yeah, there's no shells. It can't move to another shell because it isn't. So it's just a more excited state. So at a very simple level, you could think about it vibrating more, but that's not really a very good explanation. So to understand it, you need to learn, or you need to know quite a few extra things. And actually, there's a couple of models of what's going on. So one explanation isn't necessarily 100% correct, but there's two simple explanations, and I'll give you both of them. One is that there are other quantities, such as angular momentum, and we're talking about, this is quantum, so not necessarily what you think of as normal angular momentum. And there's also spin as well. So it could be that what we're actually doing is changing these quantities. So for example, we might have some protons, and we're talking about energy here. We might have protons that have spin down, okay, and then we give them some energy, and it might be actually that they turn to spin up, right? Which means that potentially they have a higher energy level. Or we might be increasing the angular momentum, which is another quantum number. So I don't know if that necessarily explains anything, because these probably don't make that much sense to you. Another perhaps better explanation, but again, it relies on more knowledge, is something called the Pauli exclusion principle, which basically states that you can never have two particles that are exactly the same in the same place at the same time if they are a certain kind of particle. So what that means is if you have two protons and they have exactly the same quantum numbers, so charge is 1, angular momentum is 1, spin is a half, spin is a half. These can't exist in the same place at the same time. So what you have to do to pack them all in the nucleus is you have to start changing these numbers, and you have to basically make one, have an angular momentum of 2, for example, and then you can put them next to each other, which means that they have these kind of excited states, and instead of putting all the electrons in the lowest, all the protons in the lowest one, you then have to start putting them in higher energy levels. Whether that means anything to you or satisfies your question, I don't know. But perhaps what you said at the start is the best. They just are excited. They just have more energy. They vibrate more. That's enough understanding, I think, to make sense.
So is it a case of the whole nucleus gets excited by the same amount, or different particles within the nucleus get excited by different amounts, and then you take like the average of them?
I think it's best to think of the whole nucleus being excited. That makes more sense, I think, at this level. I'll put a link to a longer explanation that was not too complicated that I found.
Okay, thank you.
So how would this be represented? Probably something like this. So you'd probably see these things drawn something like this diagram here. So you've got some nucleus, it emits some particles, it turns into another nucleus, and then that nucleus moves down energy levels. So I'm going to share my screen with you. So you should be able to see this PowerPoint. And, this might be a typical question. So it's a very slightly different presentation, this one, but basically the same. Got the excited state of arsenic-77. Also decays to the ground state via an excited state, which is 0.2 MeV above the ground state. So we've got a germanium atom, which decays by gamma decay to a lower energy state of germanium. It then emits a beta particle and turns into this new nucleus of arsenic. The arsenic then decays to the ground state. And so calculate the energies of the photons emitted in this decay. So this energy gap is 0.48 MeV, and then we know that that is obviously going to be equal to HF over lambda. Sorry, HC over lambda. Right, just like if this was a year 12 question on electron transitions. You'd obviously need to convert that to EV from MEV, but otherwise it's exactly the same. All right. I don't think they get much harder than this. I don't think this is a particularly hard topic. Just want to show you a couple of quick things. One is that just like when we look at electron transitions and an emission spectra of electrons, we can do the same for the nuclei. So this is a graph of energy of gamma rays against basically frequency, or how many photons. And you can get a nice spectrum like this. And you see that certain elements have certain peaks at different points, right? Which is one way we can identify what elements are in a radioactive sample. If we're getting a very strong peak of 380 or 360 kiloelectron volts, then there's it's going to be iodine. It won't be any other element. This is a fingerprint or a signature, just like neon or sodium has a very specific emission spectra for photons. And then if we zoom in on one, this is cobalt. This is just one further example where it's got a very definite signature. All right, we've got a very, very tiny, like 0.1% of photons of these energies, but basically 50% of them are these two energies here. So if something is emitting these two energies, it's going to be cobalt 60. So, I mean, it's possible they could give you diagrams like this and say, work out the wavelength of these emissions or something. But it's not at all complicated or hard in any way. Are there any more questions? All right, could you please open the worksheet for today's lesson and start to complete the questions? I'm going to find the link for Melos. I'll stay around for about 5 minutes in case you've got any questions, and then I have to go to a meeting, so I'm just going to let you carry on with the questions. Tomorrow, so not later today or tomorrow, I'll put the answers up for you to go through, and you should also go through the answers for yesterday's lesson as well, which I've put up on the lesson now.
So will you email it to me or put it in the chat?
I'm